is that rho square minus rho minus L square minus L is equal to 0, and this I can further write that implies rho square minus rho minus L into L plus 1 equals 0, which is a quadratic equation like ax square plus bx plus c is equal to 0. And we know that how to solve a quadratic equation. The solution of a quadratic equation is that x will be equal to minus b plus minus b square minus 4 x equal minus b plus minus b square minus 4ac by 2a. So I can write from here that means these will be the x plus minus values. Here our a is equal to 1, our b is equal to minus 1, and our c is equal to minus l into l plus 1. So this gives us the rho plus value by putting these values, as we have already done this. So let me write briefly. Rho plus value is L plus 1, while rho minus value is minus L. So we have from this that our u of r, was actually, then from here the two roots are here, so I will write u of r now, which is r to the power rho. So this will be equal a r to the power rho plus and plus b r to the power rho minus, and then I can write that u of r is equal to a r to the power rho plus is L plus 1 and plus b and r to the power minus L. Now the phi is actually, the phi portion we have written is the phi which was dependent on r. It was actually equal to u over r. So 1r for getting the phi value, it is to be divided by 1r, and this will make our equation is equal. A, r and 1r now, so this will cancel, and we will have a r to the power l plus b and r to the power minus l minus 1. The r will go up, so this will be minus L plus 1. This will be the solution to our radial dependent function potential, where L is yet an undetermined constant. Now our theta dependent part is actually, this was alpha square. So we wrote for alpha square L into L plus 1, then this is the theta dependent portion. This one seems to be theta dependent, but here it is having the m as well, which is dependent on phi too. So we are having this equation, and now from this equation, let me multiply p with all of this. So we will have 1 over sine theta d over d theta sine theta dp over d theta, and plus L into L plus 1 minus m square by sine square theta, and taking p is common and equal to 0, and this we call the generalized Legendre Differential Equation. So we will now solve this equation, but we want to have a change of variable in order to move from the sine and cosine to x. We know that when we are having a circle is a two-dimensional sphere. So for when x is equal to r cos theta, this is the Cartesian coordinate, here are the polar coordinates, and y is equal to r sine theta. So if I consider a unit circle means a circle with radius 1, so we will have x equal cos theta, and similarly y equals sine theta. When I consider a unit sphere, then that will also have x equal cos theta, and unit circle or unit sphere means we will consider the normalized sphere. So in a normalized sphere we will have the x equal cos theta. And now let me do some algebra to do conversion of this equation into a definite representation. I can write that d over d theta can be written as dx over d theta into d over dx. These will cancel and we will have d over d theta. Now from here, I know that x is this and this is equal to minus sine theta d over dx. So d over d theta is equal to this. If I do multiply sine with this, then sine theta d over d theta will be equal, multiply sine with this, so minus sine square theta d over dx. Now minus sine square theta I can write is from sine square theta plus cos square theta equal to 1. I can write that sine square theta is 1 minus cos square theta. 1 minus cos square theta and d over dx. Now 1 minus cos square theta I can write is x, so this will be equal to 1 minus x square d over dx. So now I come to my equation back, that 1 over sine theta d by d theta. So I can move this sine theta here, so this will be 1 over sine theta d by d theta will be equal to minus d by dx. So it will be minus d by dx, and then for sine theta d by d theta, I can write that this is equal to minus multiplied with minus 1 minus x square d over dx, and p will come as it is, plus L into L plus 1, L into L plus 1 minus m square, and then sine square theta I can write 1 minus cos square, so 1 minus x square, and this is p equals 0. Now here this minus will cancel with this minus, and we will have d over dx of let me select this in square bracket, 1 minus x square dp over dx plus L into L plus 1 minus m square 1 minus x square 1 minus x square. Now such bracket here, and p is equal to 0. Now this is again the generalized Legendre Differential Equation, but in a different style. We replaced cos theta by x. So with this equation, now we assume the azimuthal symmetry. The azimuthal symmetry. The azimuthal symmetry is dependent on phi, and phi is a function of m here. Phi is dependent on m. Now if we are having azimuthal angle is actually phi, which is changing in the plane. So we are having the m here, means for phi we are having the representation of m here. If our potential will be the same along all the points, means for different theta it will be different, but along the pi means we consider sphere is composed of different circles. So on each circle we are having different potential, but along the circle we are having the same potential, and this we call the azimuthal symmetry. And inside azimuthal symmetry we will consider that m is equal to 0, and we are left with the equation that d by dx 1 minus square dp by dx plus n into l plus 1 p equal to 0. And this equation, let me write this one, that for azimuthal symmetry, when m will be equal to 0, we will have the equation equal to d over dx 1 minus x square dp over dx plus, here we are having plus L into L plus 1 P equal to 0. So this is the equation, and let me apply d by dx on it. So we will have first function 1 minus x square and to derivative of the second function. So d square p over dx square. Then we will have plus the second function and derivative of this. So derivative of this is minus 2x and dp over dx plus L into L plus 1 and p equals 0. So we are having 1 minus x square and minus 2xp d by dx. So 1 minus x square d square p over dx square minus 2x dp over dx plus L into L plus 1 p is equal to 0. Now here we did some conversion. While when x is equal to cos theta, then as our theta was running in spherical polar coordinates between 0 and pi, so we will have cos 0 means when I write this thing for x, then I will write less than or equal, less than or equal. As cos phi is minus 1, so I will write like this, and cos 0 is 1. So x will vary between plus 1 and minus 1. Now let me write this equation a bit more simplified form. We are having d square p over dx square, and then minus x square d square p over dx square minus 2x dp over dx plus L into L plus 1 p equals 0. And if I write this in terms of p prime, p double prime, then this will be p double prime minus x square p prime minus 2x, this is also double prime, p prime plus L into L plus 1, and p is equal to 0. And let me call this is equation 2. So this is our Legendre Differential Equation with azimuthal symmetry. So this is the generalized representation, and now we will solve this one. From this point, we will have some differences with the Jackson calculation. So I will have to treat it like this. Means over here, I will also consider the power series solution. But Jackson is taking the power series differently than I will do here. The Jackson way, I have already done in the previous couple of lectures. But now you will see that this way is very comprehensive and easy to understand. So let me consider a power series solution, means assuming a power series solution for the Legendre Differential Equation. As we know that the most suitable solution of this differential equation are the Legendre polynomials. Now we will reach the Legendre polynomials by assuming a power series solution, that how it can be. So we will have to consider a power series solution, and as the power series is in infinite series, means the infinite number of terms are there, so we will terminate our power series at some instant in order to have an exact solution to the Legendre Differential Equation. So let's consider that our power series for p, which is a function of x, is equal to a naught, then x to the power 0, then x to the power 0 will be equal to 1 plus a1, and x to the power 1 plus a2, x to the power 2 plus a3, x to the power 3, and plus a4 x to the power 4 plus, and so on, until we reach an nth term, which will be a n x to the power n, and there will be some more terms as well. Then the first derivative of this series p prime of x will be a naught is a constant, so it will become 0, and here x is equal to 1, so we will have a1 plus 2a2x plus 3a3, and it will become x square plus 4a4 and x cube and plus so on, and then we will have the nth term, and the nth term will be n x to the power n minus 1 and some other terms. Similarly, the double prime of x will be another derivative of this one. It's a constant, becomes 0 2a2 plus 6a3, and it will become x plus 12a4 and x squared plus some other terms, and then the nth term n into n minus 1 an x n minus 2, and now we will have to put all this. For p we will put here, for p prime we will put here, and p double prime we will put in this equation, and we will say that if this is equal to 0, now all the x terms which are the variables are non-zero, so all the coefficients should be 0 in order to make this equal to 0, in order to solve this differential equation. So all the coefficients should be equal to 0, and in order to find all the coefficients, we will have to write them